So in this video, we're going to learn a few properties of ionic compounds. So all of our ionic solids like sodium chloride, magnesium fluoride, they all have these predictable properties. And remember, we determined what was an ionic compound by looking at electronegativity. When the difference in electronegativity was greater than 1.7 between your two atoms, so if that's sodium and chlorine, if you subtract their electronegativities and you get something bigger than 1.7, that's when we know we're going to get an ionic solid. And what's happening is that sodium is literally taking a little electron and giving it away to the chlorine, not just sharing it, but actually giving it away. So just a reminder of what that means. So if you've got an ionic solid, it's going to have some predictable properties. One is its state. So all of these guys tend to be shiny, hard, brittle crystals. So I've got a picture of magnesium fluoride here so you can see what that looks like. They tend to be this shiny, hard shape. It looks a lot like table salt, right, with that white crystal there. They're really soluble in water. You probably know that from dissolving salt in water. It's easy to dissolve salt in water, and we'll talk in this video about how these ionic solids can get dissolved in water. When you dissolve them in water, they can actually conduct electricity. So you can conduct electricity right through the water if it has ions in it, because those ions are like these free-moving charges that will conduct electricity. And ionic solids also have really high melting points. So if, say, you had some salt dissolved in water and you wanted to boil off the water, you'd expect that would be no problem, right? Without worrying about melting your ionic solid, because something like salt melts at 800 degrees Celsius. So you could easily boil a container full of salt dissolved in water and boil all that water off. Boiling happens around 100 degrees Celsius, right? And you would still be fine to not melt your salt in that case. So why does it make this crystal structure? Like, they actually look like crystals, and that's because they have a crystal structure underneath. It just comes down to the most efficient way to pack opposite charges together. So let's go back to what an ionic solid is. So ionic solid means that we've given away an electron from one atom to the next, and that's created a cation and an anion. So in the case of sodium, right, the lithium dot diagram of sodium has just one free electron here in its valence shell. And chlorine as an atom has 1, 2, 3, 4, 5, 6, 7. And what's going to happen here is that this little electron from sodium is going to be given away to that chlorine atom. That forms a cation. So the sodium becomes a positively charged cation, and the chlorine atom is going to become an anion. It'll become negatively charged. So that's what we're seeing here. That electron has been added. It's gone from our sodium to our chlorine. It's been added here. So this chlorine anion has an extra electron, which of course leaves it negatively charged and the sodium positively charged because it lost an electron. If you've got a bunch of positively charged and negatively charged things, we know that opposites attract. So the positive will be drawn towards the negative. Those guys will be attracted to each other. And like charges repel. Positives want to get as far away from other positives as they can. So what's the most efficient way to store all those things together? Well, it would just be in a crystal lattice. Your sodiums are going to go right beside the chlorines, which will go right beside the sodiums, which will go beside the chlorines, and so on. It goes beside the sodium, goes beside the chlorine, sodium, chlorine, right? So you get positive, negative in this crystal lattice form. That might seem surprising to you because if you see just the formula for sodium chloride, right, NaCl, you read that and you think, oh, there's just one sodium, one chlorine. Where did all these other sodiums and chlorines come from? That's actually not what the chemical formula means. What the chemical formula means, sodium chloride, it means that there's a ratio of 1 to 1. So for every one sodium ion, there's one chlorine ion. But that doesn't mean there's just one sodium and just one chlorine out there. There's actually millions of them, and they're all packed together in the most efficient way they can be packed, which is in this crystal lattice form of sodium, positive, a negative chlorine, a positive sodium, a negative chlorine, and so on, all together there. So here's another picture of what it looks like. So you can see those ions trying to be as close as possible to the opposite charge and as far away as they can be from the like charge. All right, so why do these things, these crystals, actually dissolve in water? Because you can take a salt crystal and easily dissolve it in water. Well, it comes down to a type of force called an ion dipole force. And just to clarify, by ion, I'm talking about the sodium ion and also the chlorine ion. So those are the ions when I say ion dipole forces. And when I say dipole, I'm talking about water. And that's because water is a polar molecule, right? Water looks like this. It's got a positive end and it's got a negative end. The positive end here, these are the hydrogens. They tend to be positive. Oxygen tends to be negative. And it's not like those aren't ions, right? It's not like the hydrogens have given away their electron to the oxygen. It is still shared. Those are covalent bonds. But this whole side is going to be slightly negative and this whole side will be slightly positive, which actually makes water a dipole, is the term for something that has a positive end to it and a negative end to it, which is what water is. There's a couple more waters. So what those waters will do, here's our nice little crystal lattice structure. You've got your chlorine ions, those are the negative ones. Sodium ions are positive. Let's zoom in on this one little sodium ion in the top right corner here. And I'm going to bring in my water. So there's water floating around this salt crystal. So this is a big chunk of salt, right? Like as in big chunk, I mean like tiny grain that you can just barely see, right? But we're zooming right into the level of atoms here, right? So it looks big to us relative to the size of an atom. So we've got that first little sodium there, right? Sodium ion. It's positively charged. So what happens is all the negative ends of the waters are going to be attracted to it. So a bunch of waters are going to come over and pull it away. So see how the negative oxygen ends of the water are all close to the positive sodium ion. They pull it off. The same thing is going to happen with our other ions too. So this chlorine ion over here is going to get surrounded by the positive ends of the water. So this is the hydrogens on the water. This is the oxygen end of the water. That'll come close to that negative ion. I could do another one here. So oxygens and hydrogens, right? The hydrogens will come close because they're positively charged, and together they'll pull off that chlorine ion. And so on it goes until all of those little ions have been torn off of your salt crystal. So here's another diagram of it. You can see the salt crystal over here, and then here we can see here's that little sodium ion, right? And notice how it's all surrounded by the oxygens. The oxygen is the red part. That's because the oxygens are negatively charged, so they're going to be close to that positive ion. And here we've got a negative chlorine, that's chlorine over here. And notice how those positive hydrogens are all really close to the negative chlorine. They're tearing off that negative chlorine part. So the positive hydrogen side of water attracts and surrounds the negative chlorine ions, and the negative oxygen side of water surrounds the positive sodium ions. All right, so once that ionic solid is dissolved in water, it actually conducts electricity. So if you just have pure water, so distilled water, no ions in it, and you try to conduct electricity through it, nothing would happen. That's not going to work. But if you put some salt in that water, suddenly your light bulb here is going to turn on. And that's because that salt will dissolve, right? It'll split into negative chlorine ions, positive sodium ions. Now it's got some positive and negative charges that are free to move. And electricity is basically just moving charge. And so you're going to be able to send electricity through water, which is, I think, pretty cool.